When we picture the ocean, we imagine one continuous body of water, endless, connected, a single mass stretching across the planet. But that's not entirely true, because in certain places, thousands of feet below the surface, the ocean contains lakes. Not metaphorical lakes, actual lakes, with shorelines, with surfaces, with waves. Entire bodies of water sitting inside a much larger body of water. They're called brine pools, and they are among the most hostile environments on Earth. Not because they burn, not because they bite, but because they suffocate, poison, and preserve, all at once. To understand how something like this can even exist, we have to start with density. Water seems uniform to us, but small differences in salinity and temperature can dramatically change how heavy it is. Normal seawater contains about 3.5% salt. Brine pools can contain 30 to 40%, 10 times as salty. That level of salt makes the water so dense that it behaves like a separate liquid entirely. Instead of mixing with the surrounding ocean, it sinks. It pools in depressions along the seafloor. It settles, and it stays. Imagine pouring syrup into a glass of water. The syrup doesn't immediately mix. It sinks. It forms a layer. Brine pools are like that, except the syrup is lethal. Because once that water becomes hypersaline, something else happens. Oxygen stops entering. The brine is so dense that mixing becomes nearly impossible. No circulation, no replenishment, no fresh oxygen. It becomes anoxic, almost completely devoid of breathable oxygen. For a fish, that's catastrophic. A fish swims by. It crosses an invisible boundary. Its gills pull water in, but there's no oxygen to extract. Within seconds, its brain begins to suffocate. Cerebral hypoxia, disorientation, loss of motor control, collapse. And if that wasn't enough, the brine isn't just salty, it's chemical. Many brine pools contain hydrogen sulfide, a compound toxic to most complex life. Hydrogen sulfide interferes with cellular respiration. It prevents cells from using oxygen effectively, even if oxygen were present. So even organisms that might tolerate salt are chemically overwhelmed. In some pools, methane concentrations are high enough to further strip away available oxygen. This isn't just salty water, it's chemically weaponized. And yet, from the outside, they don't look terrifying. They shimmer, they reflect light, they look calm, almost inviting. A deep-sea ROV camera will approach the seafloor and suddenly encounter what looks like a lake surface. A distinct boundary, like a horizon line. And when something breaks that surface, it ripples. Just like a lake. Except what lies beneath that surface is deadly. Fish rarely enter willingly. Most detect rising salinity through chemisensory systems and turn away, but not always. Sometimes an injured fish can't sense it properly. Sometimes a predator chases prey too close to the edge. Momentum carries them forward. The boundary is crossed. By the time the animal realizes something is wrong, its physiology is already failing. Crabs and eels may slip down sloped edges. Young animals may drift too near. In the deep sea, mistakes are final, and once they die, something strange happens. They don't rot, at least not normally. Decomposition requires oxygen and bacteria. Brine pools offer neither. The extreme salinity pulls water out of tissues through osmosis. Cells dehydrate, moisture leaves, salt remains. Crystals begin to form instead of decaying rapidly. Bodies become preserved, mummified in brine. Wounds seal over as salt crystallizes. Soft tissue may partially mineralize, not stone, not flesh, something in between. Stable temperatures slow chemical reactions. No oxygen slows microbial growth. No currents disturb sediment. Bodies sink and remain. Years, decades, centuries. Some brine pools contain literal rings of preserved corpses along their edges, a boundary marker between normal ocean and liquid death. But how did these lakes form in the first place? To answer that, we go back hundreds of millions of years. During the Middle Jurassic period, regions like the Gulf of Mexico were shallow seas. Under shifting climates, some of these seas evaporated faster than rainfall could replenish them. As water evaporates, salt remains. Over time, massive salt sheets formed, kilometers thick. When the seas refilled, those salt layers were buried under sediment, mud, sand, rock. Pressure increased, and salt behaves differently underground. It's buoyant. Under immense pressure, it flows like plastic. It squeezes upward through cracks, forming salt domes. When seawater seeps into these domes, it dissolves exposed salt. The water becomes supersaturated, extremely dense, and when that brine finds a depression in the seafloor, it collects. A lake is born. Mediterranean brine lakes, like the Latelant Basin, formed this way. Ancient oceans, leaving chemical traps behind. In Antarctica, brine lakes form differently. When seawater freezes, salt cannot fit into ice crystals. It is expelled, a process called brine rejection. The expelled brine becomes denser, colder, heavier. Sometimes it pools instead of dispersing, creating isolated hypersaline lakes beneath sea ice. In tectonically active regions like the Red Sea, seawater seeps downward into fractures. It dissolves buried salt deposits. It encounters magma heats, rises again. Superheated mineral-rich brine emerges and settles. 3 formation mechanisms. Same result, an underwater lake that kills in seconds. Among the most infamous is the hot tub of despair in the Gulf of Mexico, roughly 100 feet wide, about 1,000 meters deep, salinity near 40%. At the upper chemical limit for salt dissolution. Beyond that, a salt would simply crystallize out. It cannot become 60% or 80%. There is a ceiling. Water molecules can only hold so many dissolved ions before saturation. The hot tub is brushing that ceiling. And despite its lethal chemistry, life exists there. Not large life, not fish, microbes, extremophiles, bacteria and archaea that do not rely on oxygen or sunlight. Instead, they metabolize sulfur, methane, toxic chemicals. Chemosynthesis replaces photosynthesis. White bacterial mats form along the boundary lines, fuzzy carpets marking the safe zone. Tube worms gather near the edges. They do not eat in the traditional sense. They host symbiotic bacteria inside specialized organs called trophosomes. The bacteria process chemicals, the worm benefits. Crustaceans and polychaete worms hover at the margins, not inside the brine, but at the razor-thin boundary layer. Because where two extreme environments meet, energy gradients exist. And where energy gradients exist, life finds opportunity. Brine pools are chemical frontiers. But scientists are interested in them for another reason: astrobiology. Conditions inside brine pools: high pressure, zero oxygen, chemical toxicity resemble environments believed to exist on ocean worlds like Europa and Enceladus. Beneath icy crusts, vast saline oceans may exist. If life can survive here, perhaps life can survive there. Brine pools become test cases, simulations of alien seas. And then there's energy. The salinity gradient between normal seawater and brine could theoretically power osmotic engines. Water naturally moves toward higher salinity through membranes. That movement generates pressure. Pressure can spin turbines, a death lake becoming a power source. They are also geological time capsules. Because they lack mixing, sediment layers remain undisturbed. Each layer preserves environmental records, rainfall cycles, volcanic ash, tsunami events, climate shifts, stacked quietly, waiting to be read. So brine pools are paradoxes. Approach too closely and they are lethal. Study them carefully and they reveal Earth's past. And perhaps the universe's future. They are reminders that danger doesn't have to move. It doesn't need teeth. It doesn't need fire. Sometimes it just needs chemistry, a boundary line, and one small mistake. The ocean doesn't always kill with violence. Sometimes it kills with stillness. And in the deepest places on Earth, there are lakes that wait.